Okay, so last time where we left off was our discussion of showing the field axioms from these projective plane axioms plus Pappus and Desargues. Um, so maybe I'll remind you the thing that we are or the full list of properties that we want these operations we're constructing to have is this. So this is the full list. Now, it turns out that basically, the trickiest the trickiest laws to talk about here are the commutative laws and the associative laws. The other field axiom laws are basically going to fall out immediately from our construction of these two operations. These are the tricky ones. Okay. And so, remember the nice thing about this is that the list of field axioms that we had gone over before is a list of 9 properties, but our list of projective plane axioms is only like 3 axioms, right? It's only 3 things that we list out. Plus, we're assuming Pappus and Desargues, so that's an extra 2. If we were really trying to be as short as possible here, we could assume Pappus, and it turns out that the Pappus theorem implies the Desargues theorem. And so, basically, if you wanted to view it like this, you could think of our our list of projective plane axioms along with Pappus and Desargues as being kind of like a much more efficient list, since we're going to show by the end of all this that you get the exact same thing by doing it this way. That we get this coordinate system that didn't involve us bringing numbers in from outside. Right, so that's the important bit. So what I want to do now is prove the commutative laws. So what is the proof of the commutative laws using these operations that we've constructed? So let's do multiplication first. So let's construct so let's draw our typical x and y axes here. Okay. So this intersection point is my origin. I choose points 1 on the x and y axes, so there they are. So there's 1 on the x-axis, there's 1 on the y-axis. I draw my correspondence line connecting those 2 points. Okay, so I'm happy with that. And then I'm given 2 points A and B. So here's A and here's B. And now I want to construct B times A. Right? How would I go about doing this? Well, let's recall how A times B was constructed. I think I have that slide from last time. Here we go. Okay. So, how was A times B constructed? So, I have A and B here. I drew in dashed line from A to the other point in my correspondence line between the 1. So I drew dashed line from A to the 1 on the y-axis. Then I drew a solid line that was parallel to my correspondence line for the 1's here from B to some point on the y-axis, and then I drew the dashed line from that intersection point on the y-axis with that line that was parallel to this line that I drew for A, and where that point intersected the x-axis is A times B. Okay, so then how do I construct B times A here? Right, well, here what I would do is I would draw this dashed line, except I would draw the dashed line from B. Right, I would draw the dashed line from B to 1 on the y-axis. Then I would draw the solid line from A to some point on the y-axis that was parallel to this correspondence line for the 1's. And then I would draw the dashed line from that intersection point to some point on the x-axis, and that would be B times A. Okay, all right, so let's see how this goes. So first I draw dashed line from B to 1 on the y-axis. All right, so that's what that looks like. Next, I draw solid line that is parallel to the correspondence line for the 1's from A to some point on the y-axis. Okay. And then I draw line, it will be a dashed line from this point on the y-axis that is parallel to my line, my other dashed line drawn from B to 1 on the y-axis. And what I get when I do that, maybe that's a little bit off, but you get the idea. This point is then B times A. Okay. So let me see if I can fit them on the same page here. Well, if I fold this, I can. And so here's my construction. So here's my construction of A times B. Right, here's my construction of A times B. And here's my construction of B times A. Now, seeing them on two different diagrams like this, the idea is these are just different constructions, right? There's no reason a priori to think that these two constructions yield the same point on the x-axis at the end, right? So this first construction yields the point that we've called A times B. That's how we've defined multiplication here. And this second construction yields this point B times A, using our same construction. And looking at those things, there's just no way of telling that those should be the same point. The reason for that is that it requires some extra thinking, or it requires really some extra reasons to get you there. Okay, so what are those extra reasons? So let's see how this works. I'm going to, on this same, let me try to do this on the same, maybe I'll draw it with a red pen instead. So on this same picture, let me draw in A times B. So on the same picture, I want to draw in A times B. So remember, to draw in A times B, maybe I'll bring this back just for a second. So let me move my straight edge. So if I bring this back just for a second, I need a solid line on B, from B to some point on the y-axis that is parallel to my correspondence line from 1 to 1. Okay, so I need that here. And then I need to do the same construction I did for A times B here that involved dashed lines from A to 1, and then from whatever this new point of intersection is to our point A times B. So I want to try to copy this construction onto this diagram. So let's do that. So then I draw a solid line from B to some point on the y-axis. And this is parallel to my other two correspondence lines. Okay. And now I draw a point from A to 1 on the y-axis. So I draw a line here. Okay. And now, what I want to claim that if I draw the line that is parallel to this line from this point on the y-axis, okay, to the x-axis, this line is going to pass through this point B times A. So it is uniquely going to pass through that point. But that construction line that I've drawn is the one that constructs A times B. And so if that is the case, if indeed this is the line I get that is parallel, it looks like it from the picture, but of course just looking like it from the picture is not a proof. But I claim that when I do this, well, that means these 2 points are equal. And so B times A is equal to A times B. So I have a bunch of points in a particular configuration. What do you notice about this? So note, in particular, the configuration in question, I'm not going to draw further on this diagram, that I'm talking about, ignore the correspondence line between the ones. So ignore that. What is that configuration that I have? That's the Pappus configuration, right? That's the Pappus hexagon configuration. That is exactly what I'm talking about when I say the Pappus configuration. So note, this is the Pappus configuration. And when we have the Pappus configuration in front of us, what is meant by that, or what is the result of having the Pappus configuration, is that these two lines that I've drawn in red here are parallel, right? They're guaranteed to be parallel. So it is the opposite thing. It's that if I draw in these lines in a way such that these points match up, then those lines are guaranteed to be parallel. And so this is like the reverse direction. If I, constructing A times B on this diagram, I drew this line to be parallel. The question was whether or not this parallel line drawn in this way actually passed through that point. The Pappus configuration, and using the Pappus theorem, is the opposite thing. We draw in the line in such a way that it definitely passes through that point, but now our question is that the same as the parallel line we drew? The Pappus theorem says yes, it is. So by the Pappus theorem, this is exactly the thing that we need. And so the Pappus configuration is the one, it consists in exactly these lines drawn like this, ignoring the correspondence line for the ones. Okay. i.e., A times B is equal to B times A. And so, long ago when I first introduced the projective Pappus theorem, or the Pappus hexagon theorem, this, I spoiled the fun, I spilled the beans back then by saying that it turns out this is going to give us commutativity for multiplication for us. Here. Okay. All right, so let's do the same thing for, so this is for multiplication. All right, this is the commutative property for multiplication. Let's see how this works for addition. Okay. So let's do a similar construction now. For a plus b is equal to b plus a. So there's my y. Here's my x-axis. So here's x, here's y. Here's their point of intersection, which I'm calling O. I choose a parallel line L. From last time, we saw that it doesn't actually matter which parallel line to x you choose here. So here's my parallel line L. Okay, I have points A and B. Okay, how do I construct these things? So first of all, I need parallel lines to the y-axis. Ooh, that doesn't look too good. Well, it's okay. We'll try to salvage it. Those don't look quite parallel, but that's okay. We'll have to use our imaginations just a tiny bit here. Okay. So, then what is my method of constructing a plus b or b plus a? So I need lines from both a and b. I'm going to do the dashed line from b here. I'll construct b plus a first. Okay. And then I would use the dashed line from A that is parallel to this thing. And that point is that thing is B plus A, right? So let's recall how we did our original construction of A plus B. Right, so here's our construction of A plus B. Okay, so A plus B, to construct that, we had our parallel line from B that's parallel to the y-axis, intersects the parallel line to the x-axis, L, at this point. I draw a dashed line from A to the point of intersection on the y-axis, and then I draw a corresponding dashed line that's parallel where that intersects the x-axis. That was A plus B. So we constructed B plus A here using a similar way. Again, a priori, this is just a different construction, so there's no reason why those things should match up the way they do. So then let's see what it is that's going on here. Let's draw in two other lines. So I need lines connecting A to this intersection point Y. Okay, and now if I draw the line that is parallel to this line, does it actually pass through this point? My claim is that it does. Said in the backwards direction, if I draw in a line from L that passes through this point, is it parallel to this other red line? Okay, and that is answered again by the Pappus theorem. Okay, so note, once again, this is also the Pappus configuration. So this is also the Pappus configuration. And so this line drawn in that passes through the same point is in fact parallel, and so this point constructed is both B plus A and A plus B. Okay, and so A plus B is equal to B plus A. All right. And thus, our commutative laws come directly from the Pappus theorem. Okay? So this is indeed the same point. All right. So that gives us our commutative laws. Okay. The next tricky laws are the associative laws. Okay. So what do I mean by that? Well, the associative laws are a little bit more annoying to construct. To see why these things work out to the way that they are. Well, maybe I'll do the first constructions of these things, and then after I've done those constructions, I will show you the combined diagram to see why these things are equal. So maybe I'll do, as I said, I'll do the two constructions. So what we're wanting here is a proof of the associative laws. All right, so let's do prove the associative laws. The associative laws, let's do the one for addition first. The one for multiplication is similar, but we'll see both of those diagrams. So A plus B plus C is the same thing as A plus B plus C. Okay. All right. Okay. And so, let's do these constructions. So there's my y-axis. For my x-axis, how long does it need to be? That might be long enough. So here's my second y-axis and x-axis. That's a little crooked. That's okay. Okay. This is my y-axis, my x-axis. Here's their point of intersection O. Same thing down here. Okay. So let's take 2 points. So here's A. Here's B. Let's take them in pretty much the same position down here so that our diagram will look nice. Okay. So up here, I'm going to construct A plus B plus C. I'm going to construct the left-hand side on the top one. And then I'm going to construct the right-hand side on the bottom one. And then we're going to have a look at the combined diagram to see how this works. Maybe I'll be able to draw it on one of these without it looking too bad. Okay, so let's see how this goes here. So what do? First, I need my parallel line L. So let's draw in my parallel line L here. And draw in roughly the same L here. All right, so here's my line parallel to the x-axis. Okay. And so now I'm going to draw points. I need C here. I need A, B, and C. So let's put my point C like here. Okay, so there's C. Okay, now if I'm going to do A plus B plus C, I need to construct B plus C first. So how does that go? So I'm going to draw in my line parallel to C. So I'm constructing B plus C, not C plus B, although we know from the previous fact, the commutative property for addition, that I could actually do it in either direction, but I'm not going to do that. I'm going to respect the order that this shows up here. And so I have parallel line from C to y-axis. That doesn't look quite parallel, but just bear with me. Then I'm going to draw the dashed line from B to this intersection point on the y-axis. So this is me constructing B plus C, right? So then now I draw a dashed line from this intersection point on L to the x-axis, and when I do that, the intersection point is going to be B plus C. All right, so this intersection point is B plus C. Okay. So now I need to construct A plus B plus C. So how do I do that? Well, now I need another parallel line from B plus C to some point on L. But of course, I don't draw in the same dashed line because that would be B plus C. I need another line from A to this intersection point. So I'll use a red solid line here. So I have my red solid line from A to this intersection point. And if I draw in red solid line from this point that's parallel to that, that should be A plus B plus C. Right. So what is this point here? This should be A plus B plus C. So this point is A plus B plus C. Okay. All right. Okay, so let's do the similar thing down here to construct A plus B plus C. And so I'm going to, in order to do this, I'm going to draw in again, I need to do A plus B first. So I'm going to draw in parallel to my y-axis from B to some intersection point on L. That's close enough to be in parallel here. Okay. And so now to construct A plus B, I need intersection line from A to this intersection point where this thing intersects the y-axis. And then I draw in parallel to that line from this intersection point on L. So that would give me A plus B. Right? And now I need to add C to that. And to add C to that, I need to draw in a parallel from C to L. Okay. And now, what do I need? I can't draw in another red solid line here. I can't draw in another red solid line here that would be parallel to these two, because if I did that, what would that construct? That wouldn't construct A plus B plus C. That would construct A plus B plus A, right? So that's no good. And so what I need here is a line from A plus B to Y. Or from A plus B to this intersection point of Y. I'm going to draw this like a dashed red line. So make my diagram nicer here in a second. I'm going to draw this like a dashed red line. Okay. And once I've done that, now I need to draw in a dashed red line that's parallel to this one from this intersection point from C to L, and I'm done. And that would construct A plus B plus C. So let's draw this in. And what we get here is A plus B plus C. Okay. Okay. So, just look at those pictures for a second. What do you notice? Again, these are different constructions, right? They're just different constructions. And so, if these actually construct at the same point, that is a coincidence, right? In fact, this is a special thing. This is going to require some additional reasoning, okay? Well, what additional reasoning does this require? Well, I'm going to try to complete one of these diagrams to make it into the other, okay? And so, how am I going to do that? I'm going to take this picture and I'm going to draw in, I'm going to do it on the second diagram, and I'm going to draw in the missing type of line. So there's a reason why I was trying to be very meticulous with which type of line I drew in here. So I have solid blue lines here, solid red lines. Those occur in both of these. But in the top I have dashed blue lines, but I don't have any dashed red lines. In the bottom I have dashed red lines and no dashed blue lines. So I'm going to draw in dashed blue lines here that correspond to the same construction lines that I used here, right, in the first example. So I'm going to draw in the dashed blue line here. Okay. And then the corresponding dashed blue line connects what to what? Well, B plus C doesn't really exist in this picture down here. So I would draw it from C, or from this intersection line from C to L, and I'm drawing it parallel to my other dashed blue line. That's close enough. It's not the best. And what is this point? This is B plus C up here, right? So this point is missing from this second picture. Okay. Well, now I can draw in the solid blue line from B plus C to L that's parallel to all these other solid blue lines. Okay. And so then to construct my last thing that constructs A plus B plus C, I have to draw in a solid red line here, right? That's the only thing missing between these two pictures, right? So the only thing missing between these two pictures is this solid red line, and that will finish my construction of the left-hand side. Okay. Now, I'm going to return to the question. One, I could draw in this parallel line and say, does it actually pass through this point? It looks like it does. Does it actually pass through this point? The opposite question to ask, which is actually a little bit more rigorous, is to say, if I draw in this line that passes through the point in question, is it parallel to my other solid red lines? And the answer is going to be yes, and it's going to be yes by, you could probably already see it here, but I'm going to draw this in. So what is this? This is, I have just constructed here, maybe I'll draw it in red. So I've just constructed A plus B plus C in the same way that I did up here. Okay, but what do you notice? I'm going to delete some lines here. I'm going to delete that line, and we're going to delete that line. What do you notice about what's left? This is the scissors theorem configuration. All right, so this is the scissors theorem configuration. What did the scissors theorem configuration say? Now, I just drew in this solid red line, but imagine this solid red line's not here. The scissors theorem says if you have this configuration where you're missing this solid red line here, if you draw in that solid red line, then that is parallel to the solid red line over here. So if you have, and of course, remember, it didn't have to be that exact combination. If you had 3 pairs of parallel lines in that scissors configuration, then the 4th pair you want to draw in is also parallel. That's what the scissors theorem says. Okay. Yes, I'm getting a question in the chat. Well, if you have a question, you can ask it whenever. Okay, so this is the scissors theorem. And so what this says is that this line we've drawn in is parallel. So this line drawn in this way is, it passes through this point, and so these 2 points are equal, right? So the 2 points constructed in this way are indeed equal, and so A plus B plus C is equal to A plus B plus C. Okay. All right. So that gives us associativity for addition. Now, you might complain for a second and say, wait, I thought, when you spilled the beans earlier, when we were talking about this stuff, you said that this required the Desarg Theorem. And it does. It does because the scissors theorem is a consequence of the Desarg Theorem. So the Desarg theorem implies the scissors theorem. Scissors theorem is like is a convenient form of it for us, because as you see, it doesn't seem like it would be the case, but this scissors configuration actually happens quite a bit in projective geometry. Okay. All right. So we've seen it for addition. Let's see how this works for multiplication. Now, to save myself some time, rather than do 2 different constructions and then try to put them on one, I'm just going to try to do it all on one. So let me make sure that I draw this large enough. So we're looking at here A times B plus C, or sorry, A times B times C, we'll get to that, is equal to A times B times C. So the associative property for multiplication. Okay, so let me make sure I make this long enough. That should be okay. If it's not okay, we'll just extend it later. So if this is my y-axis, this is my x-axis, this is my point of intersection O. Okay, now to try to make this work out, I'm going to choose my ones that are pretty close to each other over here. So here's my 1 on the x-axis, here's my 1 on the y-axis, and I'm going to connect those with solid blue line. Okay. Now I need A, B, and C. So here's A, and here's B, And let's put C not too far away. Let's put it like right here. Okay, I think this might fit. We might have to extend it a little bit. Okay. And so, how do I construct, let's see, we're wanting to do A times B times C. So let's construct B times C first. So if I draw in solid lines for B and C, correspondence lines, I don't need both of them yet, but yeah. So there's one for B, and here's one for C. Okay. Now, if I draw the, say, dashed blue line from B to the one on the y-axis, if you're confused about what I'm doing here, just remember real quick how we construct multiplication. So I have the original one here, right? So if we're doing A times B, we draw a dashed line from A to the 1, solid line, correspondence line, parallel to the correspondence line for the 1s from B to the y-axis. And from that intersection point, we have a dashed line that is parallel to my dashed line here from A. So we're doing B times C first. So I draw a dashed line from B to the 1, so then I need to draw a dashed line. It might be a little bit confusing because I already drew in this line knowing that I would need it. But I'm not using it right now. So you can ignore that if you want. So then I'm going to draw my dashed line from this intersection point at C. That's going to give me B times C. I'm going to draw in dashed blue line here, parallel to my other dashed line. So that gives me, those don't quite look parallel, but just bear with me. So here's B times C. Okay. All right. Now to construct A times B times C, I need a correspondence line drawn from BC to the y-axis. Okay. And now I'll draw it as a solid red line from A to 1. And now I need solid red line from this intersection point to somewhere on the x-axis. And that's going to be A times B times C. Let me extend this x-axis a little bit more. That should do it. Now I want to draw in a line from this intersection point on the y-axis to some point on the x-axis, this line is going to be parallel to the other solid red line. Okay. And so what does this construct? This constructs A times B times C. Okay. All right. Okay. How do I construct the right-hand side? So for the right-hand side, I need to first construct A times B and then multiply that by C, but the multiplication is going to be on the right here. So again, recall how multiplication is typically done. So I have my choice of ones here. I have A and B. To do A times B, draw a dashed line from A to 1 on the y-axis. Draw a solid line from B to y-axis that is parallel to this correspondence line. And then draw in the dashed line from that intersection point the x-axis, that intersection point is a times b. Okay? So that's how we do a times b. Remember, so earlier in this video, I constructed b times a, if you want to go back and have a look at that, but then I messed up that diagram by, adding more stuff to it. Right there it is. Okay. And so, how does this work? Well, what do I need here? I need to construct a times b first, so let's construct a times b. So I have a and b. So constructing a times b, literally I just had that on the screen. I need a line from a to 1. I already have that. That's my solid line here. And I need the same solid line that goes from this intersection point for this correspondence line from b to the y-axis to some point. So that's what I need here. I need a solid red line here that is parallel to the other red line I have. There we go. Right there is my A, B. So there's AB. Okay, but now I need to do A times B times C. So what do I need here? Well, when I'm doing thing times thing, I need dashed line from the thing that's going to be on the left, first of all, and then whatever I'm multiplying it by on the right, I need to look at its correspondence line and then draw in the dashed line that is parallel to the first dashed line here. So I need a dashed line from A times B to 1 on the y-axis. I'm going to make that a dashed red line. Okay. And then to multiply that by C, I would need a dashed red line from C that is parallel to it. Or when I say from C, I mean from the corresponding point for C on the y-axis. Hey, what do you know? What do I get here? I get A times B times C. That's what I've constructed. Now it is clear what's going on here. Ignore this and ignore these two lines. And what do I have here? Let me make sure that that looks right on camera. Yeah. This is the scissors configuration again. Right, note, this is also the scissors configuration. So this is the scissors theorem configuration. And so these points constructed in this way are the same point. Right? Viewed another way, when I draw in that last construction line, whether it's the solid red line or the dashed red line, when I draw in either of those construction lines, I could view them as I draw in that line that passes through the point in question, and I ask, is that line parallel, to the other corresponding line that it needs to be parallel to? And the answer by the scissors theorem is yes. And so what this means is that A times B times C is equal to A times B times C. And so we've shown the other associative property, the associative property for multiplication. Okay. So we have shown today the commutative properties for these operations that we've talked about. We've shown the associative properties. These are the most interesting ones. Now we're going to do the distributive property on Monday. We'll finish with the distributive property, and then that will do it. That will be all of the field axioms, all the other field axioms fall out immediately from the definition. And so we will have done it. We will have constructed coordinates without using numbers, without bringing in numbers from outside. Okay, they're actually sitting inside the projective geometry itself, plus, so all we needed were the projective plane axioms and the Pappus and Desarg theorem. So it turns out that we can do the same kind of thinking for projective spaces, but it's actually not quite as interesting because in projective spaces you always have the Desarg theorem. You always have the Desarg theorem in projective spaces, and so in projective spaces what can go on here is actually not quite as interesting, talking about this axiomatically. So I'll do a whole discussion next time that basically discusses a bunch of consequences of what all this means. And you're going to have homework that I'll assign later today that is going to involve constructing and having a look at certain types of projective planes that are special. So for instance, you're going to have a look at a projective plane where the Desarg theorem is not true. Okay, this is called a non-Desargian plane. Okay. So anyway, I will post that later. So I will see you all on Monday.